簡単な自己紹介を自分の方からさせていただきたいと思います。アランさんはブラジルで子どもの心筋障害や発達障害について学ばれた後、2005年から日本の奈良先端科学技術大学にて情報科学を専攻され、その後5年間沖縄先端技術大学にて勤務され、現在は玉川大学にてですね、神経ネットワークや脳科学について専攻されております。ではアランさん、講演の方よろしくお願いします。
Hi everyone. So, first of all, I would like to thank you guys for inviting me here to give this talk. And recently, I've been working in social neuroscience. But I'm going to show you today some results that I did for my PhD. And yeah, so I saw today that many people are interested in robotics for multiple uses, such as human communications or support for people with pathologies. But there might be two ways in which we can study robots. So the first one is like robots that they somehow have human-like cognitive abilities, but it's not really a human cognitive process. It's something like cognitive process. Or the second way is robots which have cognitive abilities, but those abilities are based on brain principles. So probably these are the type of robots that can have similar cognitive processes and emotional processes similar to humans. So for my research, what I was trying to understand was, if we want to make robots that behave like humans, maybe their mechanisms, their algorithms should be similar to humans, such as for learning process. And if you go back to the literature of human behavior, so humans transit from like naive process for initial state of learning, and then after many practice, they become experts. So they can do some skills. They can perform some skills very, very quick, and very fast, and very accurate. So one possibility to make robots with human cognitive abilities is to understand how those mechanisms change for action selection over time. So of course it's not a new idea. So we have here in the center here Rich Sutton, which is the father of reinforcement learning theory, and of course many years ago he came up with an algorithm based on reinforcement learning, in which he suggests the same algorithm can implement learning, planning, and reactive behavior. So basically, learning, planning is some kind of habitual behaviors. Reactive behavior here doesn't really mean habitual, but we can borrow the concept from psychology in this case. So I hope you guys can see here, but if you just change some parameters of the algorithm, so you can easily simulate a learning curve here, which is very slow, if the robots or the agent is only learning. But if you change the algorithm in some ways, the learning curve, as you can see here, this line here goes faster. And if you change in many more ways, the learning curve can be much faster. So it's a very interesting, because only one simple algorithm can generate multiple behaviors in this case. So my idea was trying to understand how humans learn motor skills, and what are the brain mechanisms behind the different motor skills. So if we go back to the literature of human learning, so the classical ways is to classify learning stages into two steps. The first one, initial learning stage, as you can see here, and the final one, which is the later stage, here called advanced stage. So the basic idea is that in the initial learning stage, humans use hardcore cognitive process to accumulate knowledge of the environment. And as you become expert, so you don't need any more cognitive process, you use automatic processes. So, and in terms of brain function, as you can see here, if you consider this y-axis here, the brain activity, and this x-axis here is the time, you can see that some brain areas like decrease activity over time, and other brain areas increase activity over time. So people have done a map of what are those brain areas that show higher activity in the initial stage and higher activity in the later stage. So today we know very well which regions are activated initially and some regions which are activated later. But again, if you go back to more recent data, including old research as well, so some people have proposed that there is not only one initial learning stage and then one advanced learning stage, there is also one intermediate. So some people have mapped this intermediate stage something like anticipation of prediction. So you have accumulated some knowledge in the initial stage, and then you can use that knowledge to predict future states of the environment or to prepare in advance your own behavior. So here, what I want to show with this figure here is that there is an initial learning stage, an intermediate stage, and a learning stage. So, yeah. And some people have used different tasks and found similar processes. There is always some intermediate stage. So one possibility is that when humans are learning, they are not using only one strategy, the initial learning stage, and one strategy for action selection in the late stage. They might be using something else in between during the learning process. So probably 3 different strategies people are using as they learn. So I wanted to investigate these. I wanted to understand what are the mechanisms and what could be those strategies that humans are learning. So for that, I turned to reinforcement learning. So I think many of you guys know very well. So reinforcement learning is very simple. It's just the agent interacting with the environment, and by taking an action, the environment modify the environment, such as the state, and they get a feedback from the environment. So you can think of it if you think of it in terms of time, of a timeline, you can see how the state, the action, the reward, and the future state of the environment, they change over time if you consider trial by trial in this case. So the basic idea of reinforcement learning here that I don't explain very much, but it's the use of the learning signal, the TDM, which is the prediction of how much reward the agent is going to get in the future based on the current states. Right, so I don't give details about it, but at least so far we know very well how this is implemented in the brain. It's very interesting that probably reinforcement learning is one of the first computational theories that researchers have found that has some that can possibly be implemented in the human brain. So, of course, reinforcement learning is not only for simple reinforcement learning agents. We can modify these changes in parameters and can apply this, for example, for social interaction if you put 2 agents interacting. Or we can go even further if we think about mental simulation. So like things that are going on in your mind, but you don't need the feedback of your mind. Maybe feedback is only internally. And we can use this, we can suggest something like a fictional processes that are going on in your brain. So, but reinforcement learning is not very simple, right? So there are 2 main classes of reinforcement learning, which we call model-free and model-based. So basically, model-free is a action value learning process. As you can see here, it's a very simple. It's just quantifying the expected reward based on if you use a discount factor here, and if you consider future steps. So, but for reinforcement learning, this is very simple. It's to implement. But the interesting point of this model-free strategy is that you can use this when you are learning from experience. So that's a very key point of today's talk. And if it's a very important for learning from real experience, it might be related somehow, according to my idea, to initial states of learning, which some humans are learning from actual experiences. And model-based is basically is the use of mental representations, internal representations, in which you can, based on your current action and state, you can predict what's going to be the next state of the environment, or even what will be the future reward that you're going to get. But in the case of model-based, it's a time-consuming because you might somehow estimate transition probabilities, and this is very hard for the brain. And the point here is that it's based on the prior knowledge. You can mostly use, you are most likely to use model-based if you have prior knowledge. And if you can use that prior knowledge to predict future states, you can also boost your learning. You don't have, for example, you don't have to go back from the initial learning stage to learn the same behavior. So my idea here is that, and in the end, so both, regardless of which strategy you are using, so both the strategies are going to converge to a policy, which is very similar to memory, to habit. So if you're learning using this strategy, you are going to generate a memory of your behaviors. If you're using model-based strategy, you're also going to generate, build up memories of your behavior. So my basic idea here is that maybe in the initial learning stage that I showed before, I have proposed this in a previous paper. Maybe in the initial learning stage, when performance is random, maybe humans are using some kind of model-free, value-based strategy, and then later, with experience for the intermediate stage, somehow after acquisition of knowledge, we switch from model-free to model-based, and then later after much experience, we change again from model-based to memory or the policy. Of course, if the task is very simple, if you don't have to build up very complex models of the environment, you don't need to switch from value-based to model-based. You can quickly switch from value-based to model-based. If it's just a simple stimulus response association. So I just want to say here that the transition here is not straightforward in a straight line, but you can jump steps as well. So some people have proposed how model-free and model-based strategies are used in the brain. So just very quickly, I want to say that, for example, Balain and Nathaniel Dawn have proposed that somehow Nathaniel Dawn here calls tree system, which is the estimation of transition probabilities, and they have associated the two main regions involved in this, so like prefrontal cortex, dorsolateral prefrontal cortex, and striatum, in the implementation of model-free and model-based. But the thing is that the brain is very huge, there are many brain areas. So my idea was that instead of using only basal ganglia and the prefrontal cortex for implementation of model-free and model-based in the human brain, so we might as well use the cerebellum together with prefrontal cerebral cortex and basal ganglia. So of course, this is not my idea, this was of Kenji Doyen, who was my boss in Okinawa. And so he came up with several ways in which algorithms are likely could be implemented in the brain. So we decided to test how humans use different strategies. So we defined this grid sailing task, which is very simple. You just push the buttons, and the red color here indicates the start location, start position, start state, and the blue color here is the goal. So you have to push here, buttons. So the buttons, the key point here is that the buttons are associated with different motion directions. So the idea is that you have to learn the model of the key mapping here. So the key mapping here, in this case here, the key mapping is associated with this shape here. Okay, and here, the color here changes for green, and this is the go signal. So when it's red, we call this delay time. So subjects, somehow they have a time to prepare. If they know the key mapping, if we give them about 10 seconds, so they might use 10 seconds to think and prepare in advance the sequence of actions that they have to make to move the cursor from the start position to the go position here. But sometimes we don't give them the delay time. So they just have to start the performance. So we can we can measure what is the effect of giving a delay on subject's performance. Okay, so yeah, so the interesting point as well is that there are multiple ways to reach the goal target here. So we don't force subjects to follow only one way. So each subject can learn different pathways. The only key point here is that we ask them, once they learn one specific sequence, as you can see here, we ask them to stick with the same sequence. So the idea is that if they stick with the same sequence, we can measure change in performances, such as speed of performance. What we did was, it's a bit complex here, but what we did here, we have a training day here, and we have a test day for the fMRI. So in the training day, we prepare several key mappings here, and for the training day, we choose only 2. So in the training day, subjects get acquainted. They learn how to use 2 of those 3 key maps. And we combine these key maps here with different start goal positions, as you can see here. So in the training day, subjects can learn 2 things. Either they learn sequence of actions, because they practice for many times these combinations here, and they learn the model of the key mapping. So the difference in colors here are just like the black color here are combinations of key mapping and start goal positions that we use only for the training session. But for the fMRI session, for the test session, we choose one of those 2 combinations, and we ask them to perform the same combination. And so remember that I told you that in the training session here they use only 2, and in the fMRI session we introduce a new one that they didn't practice before. So we can test the effect of knowing which key mapping you can use and not knowing the key map. So in that case, we can somehow measure the use of model-based strategy because we assume that they have learned the model of the key map in the training session, and the use of model-free strategy in the case of the new key map, which they didn't use before. So of course we did some predictions of performance and how performance could be, and I didn't want to be very straightforward and suggest what brain energy we would find if subjects are using value-based in this case, and or model-based or policy. But in the test session, you can think that, for example, for condition 3 here, we ask them to perform the same sequence of actions that they have learned on the previous day. So if they have learned well, if they have made a memory of the actions, their performance here would be very high, and no difference between delayed start and immediate start. And for condition 2 here, in the condition 2 we assume that they are using key maps that they have learned on the previous day, but we are combining those key maps with different start and goal positions. So we assume that they can use the knowledge of that key map to prepare in advance the sequence of actions for new start and goal positions. So in that case, we assume that if we give them time to think, they can use that prior knowledge to prepare in advance the actions. So we can somehow test whether people are using model-based strategies. So I don't give the details of the models here, but basically we assume that subjects are learning models. M here is the model, and the model comes from the data, which is subject's behavior, and the model can be one of the 3 key mappings. As I showed before, yeah. So we assume here that the model comes from the key mappings here. Okay. So, and then we prepare different action selection strategies that subjects might use in the experiment. So let me first show you some data of the training session so that you guys can see. So yeah, so this is the average overall combination of key mapping and start goal positions in the training session. So as you can see here, the trial here is like only 30, but they practice many more times in later experiments. So as you can see here, this is the average reward score, which is the score that they get when they reach the goal target. So as you can see here, their performance reach the learning threshold of 80% like in the middle of the experiment, and then keeps going higher up to 100%. So we just want to make sure whether this is in the training session here, and this graph here is the behavior right before the fMRI, right before the test session, because we want to make sure that they could still. So the interval time between training session here and the test session is only 1 night. So we assume that in 1 night sleep, subjects have somehow consolidated their knowledge of the memory of the actions that they have learned on the previous day. So just before the fMRI, we asked them to play 6 trials, of which key mapping start-go combination here. And as you can see here, the performance is like 100%. So no variability at all. So we assume that somehow they have a memory of the sequence that they have learned on the previous day. So we assume that they are selecting memories actions only from memory, which we call in this case a policy. What about the fMRI, in which we ask them to perform with the new key mappings here? So when we ask them to practice the experiment with new key mappings here, they can reach the learning threshold of 80% here with a delay time only at trial 7. And there is not much difference here between delayed start and the immediate start. As you can see here, this open space here. But for the condition 2 here, in which we ask them to use previously learned key mappings, they reach the learning threshold at trial 3 much faster than in this case here. And you can see there is a huge gap here. So somehow when subjects have a knowledge have a prior knowledge, and they can use that prior knowledge with new start and go positions in this case, they can speed up learning. On the other hand, in condition 3, which is we just ask them to repeat the same sequence of the combinations that they have learned on the previous day, you can see again, the performance is very high, 100%, and no difference at all between delay and immediate start conditions. So somehow the human behavior fits well to what we predicted. Okay. So then we go after what are the brain mechanisms that are implemented. So here we assume that humans are using different strategies in the different situation. So if you go back to the classical idea, only strategies people have been assuming people use, but in our case we assume 3 different strategies. So then we look for the brain mechanisms implementing those different strategies, and we want to see are only 2 brain regions involved as previously proposed before, or many more regions are involved, including the cerebellum. So for the brain imaging experiment, so we only analyze the delay time. So in the delay time, subjects have about 4 to 6 seconds. So we can compare the brain activity for condition 1 for the new key mapping, for condition 2 when they use the previously learned key mappings, or for condition 3 when they have to just remember the sequence of actions they have learned on the previous day. So in this case here, what we did, we compared the brain activity of the new key mapping with the condition 3, which is the well-learned condition. So we do the same thing for the condition 2, the previously learned key maps, and the versus condition 3. So as you can see here, similar brain regions are activated for the 2 cases when we use the condition 3 as a control. But you can see here that frontal regions here, as you can see, are much more active when subjects are practicing condition 2. So if we check the brain activity in the basal ganglia and the cerebellum, we find the similar properties. So like the blue here is for condition 2, and the orange color here is for the condition 1. So you can see that the brain gets more active for when subjects have prior knowledge, and they can use that prior knowledge during the delay time. If we compare condition 1 versus condition 2, we find this. So in condition 2, mostly dorsolateral prefrontal cortex in the right hemisphere, and the blue area here is more active for condition 2. But for condition 1, in this case here, mostly ventromedial prefrontal cortex. So if we check the basal ganglia, we see this. the ventromedial basal ganglia activation here for condition 1, and the blue areas here, the dorsal striatum active before condition 2. So in this contrast, we find that the different learning situations, humans were using predominantly different brain areas. Okay. And if we check since we were using condition 3 as the baseline for this analysis, so we want to check the condition 3 as a baseline activity. So in condition 3, mostly motor and somatosensory areas active. So even though we see here some spot in the prefrontal cortex, this is not as huge as in the other two conditions. And for the basal ganglia here, we just find this: the posterior basal ganglia and the right hemisphere of the cerebellum, which are regions involving motor memory or motor control, are activated before condition 3. So yeah, so I just made a new movie here so that you can see. So these are the regions that are predominantly activated for different conditions in our experiment. So the orange colors for condition 1 for the Nuki mapping, the blue colors for the condition 2 for the use of previously learned models, and the pink, the magenta colors for condition 3 for the use of memory-based strategies. So maybe it's time to finish, right? Yeah. So anyway, so what I can say here is that what we found is that maybe humans don't use only two strategies. We use different strategies depending on the context, and we found that different strategies are associated with different neural networks in the brain. Yeah, so yeah, so I think that's all I can tell you for today. Thank you very much. Okay, if you guys have any questions, so feel free to ask. Okay, no questions? Okay. You have questions?
What about emotion? Did you develop the same experiment using emotions? So therefore, what do you think about that?
Yeah, so I don't have a clear answer for your question, but as you can see here, the ventromedial prefrontal cortex was predominantly active when people were using, we assume value-based learning, right? And together with the ventromedial prefrontal cortex, mostly the ventromedial basal ganglia striatum was active. So if you think that learning, go-directed learning should be motivated, so you should be willing to learn the task. You are interested in the task. So one possibility is that these regions somehow are guiding, motivational aspects are guiding learning. But motivation is very broad concept. I don't know exactly how they fit to like emotion. But at least you should be happy, right, to be learning. So yeah, since these regions somehow are also involved in emotional states, so somehow emotional states are playing an important role in the initial state of learning according to our data. But I don't know how to set up an experiment about emotional processes. The question is Hiroki.
I'm interested in the Waterbased structure of activated areas in the almost last slide. In condition 1, mainly the frontal area of the whole brain was activated, and in condition 2, the medial area of the whole brain was activated, and so the position of the activation was gradually shifted from the anterior part to the posterior. Is that a general tendency or this area?
Yeah, so when I applied the brain activity for Commission 1 time course, if there were changes, right? So assuming for Commission 1, they are using model 3 initially, and then later, as they practice, we can assume that they're going to switch, right? From strategy 1 to strategy 2, and maybe the brain activity is going to change. So I did this analysis on a trial by trial basis, and we found some changes. But I think our data itself, since there were many variables together, was not very clear to make this dissociation. But yeah, of course, it's well known. So many people have shown that, especially frontal areas are more active in the initial stage of learning, and the posterior areas active when people become experts. Right. So, but in our case, we didn't test. We didn't prepare the experiment to test those changes. But maybe if I go back to the data, I can find something. But to answer your point, yes, other people, other previous studies have found a switch from frontal areas to more posterior areas. I don't know if it changes completely from ventromedial to postlateral and then posterior. That one we don't have a clear idea. Okay, finish. Good.
アラさん、講演の方ありがとうございました。この後は引き続きセッションフリーとなりまして、自由に発表聴講を行える時間帯となっております。予定の方ですが、この後から17時45分までがセッションフリーの時間帯となりますので、発表者の方、また聴講される方、準備の方をお願いします。